I was asked to review how to solve this problem that was handed out in the case study examples in class. The question is essentially asking you to calculate the estimated VO2 max in a submaximal cycle ergometer test using their work rate and their heart rate response. The calculation of this takes in two primary assumptions. The first assumption is that with increasing exercise intensity, heart rate increases linear. Of course, we should know that this assumption is relatively easy to understand and relatively easy to follow. However, it's not the case for everything. Again, we're assuming normal, but if we actually take a quick look, here's an example from your notes in Module 1.5, I believe, that kind of shows us the process. This process is using the graded exercise treadmill test as opposed to a cycle ergometer. So the calculations are a little bit different, but plotting the graph works relatively exactly the same. And so if we kind of generate or take a look at this, so what we'll see is if we look at the first half of this graph, we can see that the notes highlight that this part of the curve is what we identify as a nonlinear part of the curve. In our exercise physiology lab, I set this point at about 55% of your heart rate max. Note that that is a good number for most people who are of your age, but that's not quite the case for everyone. And so what the book suggests is the nonlinear portion is everything that is less than 110 beats per minute. So again, if you were to quickly calculate 55% of your heart rate max, you would come up with a number that is plus or minus a few of 110, and it's the reason that I use it in the lab. Here we have a hard stop on a deadline of 110 beats per minute. That way we can encompass all kinds of individuals, not just 20-somethings as we look. Outside of this range, again, we can see that assumption remains true. So we can draw, at least as best as we're capable on the computer, of drawing a straight linear line once we're above a heart rate of 110. We'll note that one of the goals, as we're kind of looking at, we're going to ignore all points less than 110, and then we're going to stop the test at 85% of heart rate max. And then what we're going to do is, since this is of course a submaximal, so that's the idea, if we're going to stop it, that's an at sign, 85%, we can then estimate heart rate max with our heart rate max being estimated at 220 minus our age. And so now we can kind of take a look at our cycle ergometer question that we had with a little bit of background. So ultimately what we're going to do is we're going to create a graph here, and we're going to graph on the y-axis, we're going to graph heart rate, and on the x-axis we're going to graph oxygen consumption. If we look at the data that we're given here, so here we're given work rate in kilogram meters per minute, also known as power, same exact thing, and heart rate. So what we need to do is we need to calculate VO2 for each of these work rates so that we can plot VO2 and heart rate as we move forward. I've given you the equation on the slide, and in the exam you will have this equation to help you calculate it. So let's quickly write it out. So VO2, again in mils per kg per minute, equals work rate times 1.8 divided by our body weight in kilograms, so I'm just going to write kilograms, plus 7. So following mathematical rules, the first thing that we're going to do is solve what's in the parentheses, then we're going to do the division, and last we will do the addition of 7. So now we can just go in and we can plug these numbers in. So I'll do it really quickly here. So VO2 equals work rate of 300. So we're taking our first number here, times 1.8, divided by our body weight, which is 81.7, and then plus 7. So when I plug this in, I get a value of 13.6. So I'm going to quickly pause the video. I'm going to do the math really quick, and then once we get those, we'll continue with the plotting of the equation. Okay, so I've completed all the math, and here's the values that I got when I calculated them. So for a work rate at 300 kilogram meters per minute, that's an estimated oxygen consumption for an 81.7 kilogram person of 13.6. At 450, it's 15.8. 600 is 20.7. And 750 is 23.52. So now what we're going to do is we're just going to take these values and then plot them against them. So VO2 and heart rate. And so typically students kind of struggle or typically have to erase a couple times on this. So I'm going to try to do it as best I can. So let's think about heart rate. We're going to need to go at least up to their maximal heart rate, which would be 220 minus 50, which is 170. So again, I'll note you don't have to start at 0. I'm going to start at 100, and then we'll go up by 10. So 120, 40, 160, 180, 200. All right. And then on our VO2, you can see again we're going to go from a range of 13 to 23. We probably need to, just to be safe, go up to 40. So let's do 5s. Kind of looking at this again, we're going to be relatively small, but that's okay. We can absolutely work with it. So now all we're going to do is plot. So the first thing that we're going to notice is that we only want to plot things that are in the linear portion of the curve. And so if we think about this first point at 100 is non-linear. So do not plot that curve and add it to your line, because it is going to then make our assumption that we have a linear heart rate response not correct. So we're just going to plot these bottom 3 points. So we can take a VO2 of 15.8 and then plot it at 110. We'll then take our next one, which is 20.7, and go to 125. And then we'll go to our next one, which is 23.52, and we'll go to 140. So the next thing that we would do is highlight then our maximal heart rate. So our estimated heart rate is 220 minus 50, sorry, 220 minus their age, which is 50, which gives us 170. So we know that as we're calculating this, our value is going to have to, our line is going to at least have to get to this 170. Again, I apologize, that's a very sloppy line. That should follow 170 straight across. And so then if we kind of use it, we can, I was hoping to see if I had a line, but now what we're going to do is we're going to draw a line of best fit for these 3 points. Again, that's relatively close. The idea is that we're trying to draw a line that takes into account and averages the distance from that line is equal for all of the points. Again, I'm doing this on a computer with a mouse, so it's not quite perfect. In the perfect world, I'd probably move this line, shift it just a little bit up. But for the idea of this, then I think it's good enough. Next, what we're going to do is we're going to say, okay, assuming that heart rate increases and that heart rate max occurs at the same time that VO2 max. So again, we're going to assume that VO2 max occurs at heart rate max. And so we have our heart rate max of 170. We would then draw the line down to our prediction here. And based on mine, we would say that their estimated VO2 max is, let's say, what is that? Maybe 32 mils per kg per minute. So the last thing that we need to do is express this value in METs. What we need to remember though is that 1 MET, running out of space here, we'll come here, so 1 MET equals 3.5 mils per kg per minute. So all we're going to do is take our estimation of 32, divide it by 3.5, gives us 9.14 METs. And that would be your final answer. So their VO2 max is 9.14 METs.